Welcome to this video on viscose versus lyocell, two important regenerated cellulosic fibers produced from wood pulp. Although both originate from cellulose, they differ significantly in manufacturing technology, fiber structure, performance characteristics, and environmental impact. Let's compare them step by step. This shows the flow chart of viscose and lyocell process. Although both viscose and lyocell start from the same raw material, wood pulp cellulose, their dissolution routes are fundamentally different. In the viscose process, cellulose undergoes chemical modification. It is first treated with sodium hydroxide to form alkali cellulose, and then reacted with carbon disulfide to produce cellulose xanthate. This chemical derivative is dissolved and later regenerated into fiber. In contrast, the lyocell process uses direct dissolution in N-MMO, or N-methyl morpholine N oxide. Cellulose dissolves physically without forming any derivative, and its chemical structure remains unchanged. This fundamental difference makes lyocell a simpler and more environmentally friendly dissolution technology than viscose. Spinning is the most critical step in fiber production because it determines the final structure, strength, and performance of the fiber. In the viscose process, wet spinning is used. The spinning dope has a lower degree of polymerization, typically between 250 and 350, and relatively low viscosity. The filaments are coagulated in a chemical bath containing sulfuric acid, zinc sulfate, and sodium sulfate. This rapid regeneration produces a fiber with a more amorphous structure and lower tenacity. In contrast, lyocell uses a dry, wet spinning process. The dope has a higher degree of polymerization, around 500 to 600, and higher viscosity. After passing through an air gap, the filaments enter a water bath, allowing better molecular alignment and formation of crystalline regions. As a result, lyocell develops a highly ordered fibrillar structure and significantly higher strength compared with viscose fiber. After spinning, both viscose and lyocell fibers undergo washing and finishing operations to achieve the desired quality. In the viscose process, the fibers are thoroughly washed with water to remove residual chemicals remaining from regeneration. The fibers then pass through bleaching, finishing, and drying stages. In the lyocell process, washing also removes residual solvent. However, a major advantage is that the N-MMO solvent is recovered and recycled back into the process. After solvent recovery, the fibers undergo bleaching, finishing, and drying, similar to viscose. This solvent recovery system makes lyocell a more sustainable production process. When comparing mechanical properties, lyocell clearly outperforms viscose. Lyocell has nearly double the dry strength and maintains excellent strength in the wet state. Viscose experiences a significant drop in wet tenacity. Although viscose has higher elongation and flexibility, lyocell offers superior durability, dimensional stability, and resistance to deformation during use. Fiber structure has a major influence on strength, appearance, softness, and dyeability. Viscose fibers have a rougher surface and an oval-shaped cross-section with a distinct skin core structure. The skin layer is denser and more oriented than the core. With a crystallinity index of approximately 0.25, viscose offers excellent softness, absorbency, breathability, and dye uptake. In contrast, lyocell fibers have a smooth surface, a nearly round cross-section, and a homogeneous fibrillar structure without a skin core distinction. Their higher crystallinity index, around 0.44, results in greater strength, dimensional stability, and durability. While both fibers are comfortable and absorbent, viscose generally provides better dyeability, whereas lyocell offers superior strength and shape retention. The environmental impact of these two technologies is very different. Viscose production requires carbon disulfide and large quantities of water, creating a heavier environmental burden and requiring significant pollution control measures. Lyocell, on the other hand, recovers more than 99% of its N-MMO solvent in a closed-loop system. No harmful sulfur byproducts are generated, making it one of the most sustainable man-made cellulosic fibers available today. However, solvent recovery does require considerable energy. To summarize, both viscose and lyocell are regenerated cellulose fibers, but their production routes and final properties are quite different. Viscose relies on chemical derivatization using sodium hydroxide and carbon disulfide, resulting in fibers with lower strength, lower crystallinity, and a higher environmental footprint. Lyocell uses direct dissolution in N-MMO without forming a cellulose derivative. This produces stronger fibers with a dense fibrillar structure, higher crystallinity, and improved performance. From a sustainability perspective, lyocell offers a major advantage through closed-loop solvent recovery exceeding 99% in the absence of harmful sulfur byproducts. Although challenges such as energy demand and fibrillation remain, Lyocell is widely recognized as the more sustainable and high-performance cellulosic fiber technology. If you found this comparison of Viscose and Lyocell useful, please like, share, and subscribe to the channel. Thank you.